In this video, we're going to take a look at a few ways to prove whether or not two triangles are similar to each other. So to get started with that conversation, let's first remind ourselves what it means for two shapes to be similar. In this first case here, one of those is visually check to see if they look like copies of each other, one larger, one smaller. That's not a technical test, but it's a place to start. So we see at these triangles, they look like they should be copies of each other. And one way we can check for that is that all pairs of angles are congruent. So we see that angle K and Q are congruent, angles L and R are congruent, and these 90-degree angles are congruent. So these triangles have all pairs of angles congruent to each other. So one way to know that these triangles could be similar would be to check all the angles. So we'll note that all corresponding angles are congruent. Okay. And then remember what it is we're checking about the sides. Sides won't be the same length, and we clearly see that here. These side lengths are different than those side lengths. But we do say the sides have to be proportional, meaning we have to have had the same scale factor to go from one triangle to the other. If you're going to divide one of these sides by 2, you have to divide them all by 2, for example. And so that's what we're going to check. And it's very simple. You look at your shape. In this case, we'll look at triangles today. They have 3 sides, so you will set up 3 ratios. And within these ratios, you'll put in your side lengths from the triangles. And being consistent here, so let's say you want to use the side lengths from the larger triangle, put all 3 of these in either the top of the fractions or the bottom. I'm going to put them in the top, and I'm going to go from lowest value to highest. So we have 16 and 30 and 34. And then for the smaller triangle, we'll put all of those in the bottom of those fractions. And there are ways that we can know where those have to go. One of those ways is you could look at the angle markings and base it off of that. But you can also do a very easy check. If you ever need to know which sides go together, just go through this. Figure out the smallest side in one triangle and compare it to the smallest side in the other. So we're going to compare 8 to 16. And we can work our way across. So we can say this is the next length up. So we can say this is the medium side maybe, and this is the medium side. So we're going to compare 30 to 15. And for the same reasoning, if 34 is the largest side and 17 is the largest side in this triangle, we'll compare large to large. And now all we need to do is check that these all reduce the same way. And you can either grab a calculator and divide them to see what they reduce to. A standard scientific calculator should do that. Simplify your fractions. In this case, pretty easy for us to tell that these all reduce to 2. And because of that, sides are proportional. And that's what we were checking. Are all of the comparisons equal? Meaning we went from one shape to the other equally. So all sides are proportional, which is good. That means these triangles are similar to each other. And we could write that similarity statement, which says triangle, let's say JKL over here, is similar to triangle. The order matters. So remember, the order tells us which angles are congruent. So if we went from J and then to K, the next one needs to go from P, then to Q, followed by R. And lastly, for our scale factor, there are 2 that we could put. We could either put 2, which is what we saw when we reduced our sides, or it's also acceptable to say 1/2, and that's all based on the order of your comparison. So whether you're comparing going from the larger to the smaller or the smaller to the larger. both of these scale factors are okay. All right, so actually with triangles, it doesn't take that much work. So we're going to spend most of our time just on triangles themselves because they have fewer components, only 3 sides and only 3 angles. And that means there's a little less work that needs to go into checking all this. And that's what we want to do. We want to get just a foundation for how to check if shapes are similar. So let's stick with triangles. So 3 theorems I have for you. One of these is called angle-angle theorem. It just so happens that if in triangles you know that 2 of the angles are congruent, it is a guarantee that the triangles are similar to each other, where one is a smaller copy of the other one. So if we're looking for this theorem, we're going to have to be able to show that 2 pairs of angles are congruent. And if we can do that, we'll say that the triangles are similar by the angle-angle theorem. Okay, so pay attention to the letters of the theorem, that they're representing angles in this case. And if you remember, if we know that 2 angles are congruent, the third pair of angles also have to be congruent because of that total of 180 that each of these would give us. But we don't have to go that far. Just seeing the 2 is good enough. All right, so let's look at a second theorem here. It's called side angle side. And in this one, notice it uses the letter A right here. And because of that, we are going to have a pair of angles that are congruent still. And if you look, we do. Angles A and Q are congruent to each other. So that would be step 1. Show that a pair of angles are congruent. Okay. And now we also have to check the sides. So the sides that we check are important. And on here, you can see there's a red side here, and a blue side here and here. And what's important is that the sides that we compare, they have to create the angle that we marked as congruent. So notice up here, we have angle A marked, and the sides that we are checking are the 2 sides that make up angle A. So it has to be those sides. That's why it's called side angle side instead of side angle, because it has to be the angle where these 2 sides meet up. So we are good to go here because these are the 2 sides I'm using. The angle that I'm looking at is where those sides are meeting. And so step 2 is going to be what we did up above, show that these sides are proportional. So show that the 2 pairs of connecting sides are proportional. Okay? And what that really means is that they have the same scale factor. Are proportional. Okay. And so once you set up that comparison, what we're really interested in is, do these reduce to the same amount, these ratios of sides? Okay, and the last scenario here is called side, side, side. And so with this one, we're not concerned about the angles. We're just making sure that all of the sides do what they should. So when we compare all 3 pairs of sides, do all of those ratios reduce the same way? In other words, do all 3 pairs of sides have the same scale factor in play? And we can check that fairly quickly. So we set up those fractions. We check, do all ratios reduce to the same value? And what we're trying to determine from that is there a consistent scale factor going from one to the other? Because if we're going to double the size of the shape, that means we'd have to multiply all of the sides by 2, just for example. Okay, and those are the 3 theorems. They just take little pieces of information instead of checking all of the angles and all the sides. So let's look at a few cases here that could happen, and we might have to pull some old information from the past. Starting with number 1, you see that there's nothing. There are no side links and no angles shown. And the only thing you're given are these arrows on segment FG and JK representing parallel lines. So if you recall, with parallel lines, so I'm going to draw these out a little bit. With parallel lines here and here, if you have a connecting line to them, the transversal, there were some special angles that were congruent. So we could talk about this transversal, for example. With that transversal, we have some angles on either side of it, such as this one and this one. They're on opposite sides of the transversal, and they are between our parallel lines. If you recall, those are called alternate interior angles are congruent, or alternate interior angles. And what we had decided in the past was those have to be congruent when two lines are parallel. So we have alternate interior angles here. You could also say that angles F and K are alternate interior angles for the same reason. So here's a different transversal connecting these parallel lines. And that would be a case of alternate interior angles here and here. And then we do have a second scenario, even though that's enough information. That's angle already. But I want you to look for these two. In the middle, these are called vertical angles. And remember, those are always congruent. So we'll look for those, see if they ever apply. And the good news is, even though we don't know the angle measures themselves, we do see that the angles are congruent to each other. So our response is going to be yes. The triangles are similar, and we can see it's FGH, which would correspond to KJH, because the order describes which angles are congruent, and the theorem is angle. Even though we showed all three pairs of angles, the requirement is just show two pairs, and that's good enough. Okay, so looking at another case here with number 2, we see in these triangles we're given some side lengths. We also are told that there's a right angle in each of them. And remember, a right angle is congruent to itself. So we could say there we have a pair of congruent angles. Okay. Here and here. So we have that pair of congruent angles here. And the question is, do we have side angle side? It depends. We have to check these other sides. So first thing to check is, are the sides that we're talking about creating that 90-degree angle? Do they meet up at the 90 degrees? In this triangle, they do. In the other triangle, it looks like they do as well. And that's the setup. It has to be that way, where the sides that we're investigating meet up at that angle that's between them. And so we're going to use that strategy we used before, where we compare the smaller side in one triangle to the smaller side in the other triangle. So we'll compare 6 to 6 and see if that's the same as the comparison going from 10, the larger side here, to 8, the larger side here. And you're going to notice that when we reduce this, we get 1 from the first ratio, and the second ratio, we get 5 to 4. So those are not equal, right? And because of that, the sides are not proportional. We don't have a consistent scale factor, so they are not similar. All right, and that's it. So if you want to leave the blanks, you can put not applicable in A. Okay. So number 3, let's look at that one. If you look at that example, you're going to see that there are 2 triangles in the picture. It's a small triangle, but it's inside of the bigger triangle, and that can be hard to visualize sometimes. So one strategy I'm showing you here is, if it's hard to visualize, what you can do is you can draw the triangle separately if it's helpful. And so the smaller triangle, it has vertices P, S, Q. And we see that there's a side length of 24 and a side length of 16. And the larger triangle has vertices RST. And if you're not careful, you'll accidentally put some incorrect side lengths here. We'd be tempted to say 12 because we haven't used it yet, but from R to S is actually 12 and the 24 combined. So that would be a combined length of 36. And going from S to T, that's 16 plus 8, that's 24. Okay. And so in this one, we only have 2 pairs of sides. And so we have to think about what theorems we are in play. In each triangle, we know 2 sides, and we have a theorem that uses that. It's called side angle side. And we need to see, in order to use that, we also need a pair of angles that are congruent. So do we have congruent angles between these 2 triangles? If you look closely, you'll see that we actually do, because both triangles used angle S. And so the angle S in this triangle is the same as the angle S in this triangle. So they both use that same angle measure. And good news is the sides that we're given meet up at that angle. So that would be the setup for side angle side. So let's check if our sides are proportional. We'll do that comparison. Smaller side here to the smaller side here. So 16 compares to 24. And we'll compare the larger side in this one to the larger side in this one. And so we're comparing 24 to 36. Check that really quickly. This one reduces to, you could divide them both by 8, and you'd get 2/3, 2 to 3. And the other, we could divide, oh, I put the wrong measurement down. That's a 36. Right, the larger side here is 24, larger side here is 36. We could divide both of these by 12, and we get 2/3. So the sides are proportional. We have a scale factor of 2 to 3. And that would mean that these triangles are similar to each other. So we're going to put yes. The theorem is side angle side, similarity. That's what that squiggle means, similarity, similar. And then the order that we need, PSQ, should correspond to RST. Okay, so there's 3 examples. Let's take on 3 more just to make sure we have everything cleared up. So a new case in number 4, you see the 2 triangles and you're only given the 3 pairs of sides. And because of that, what we're checking in the end is, does the theorem side, side, side work out? And so what we need to do is compare our sides to see if the comparisons are all equal. So going through that, looking at these, we see the smallest side in this triangle is 32. The smallest side in this triangle is 22. So we'll compare those. We'll work our way up. We could call this the medium side. Compare it to the medium side here. And then we compare the largest side to the largest side in each of them. And let's go ahead and check those comparisons. So we have 3 sides in a triangle. That means we're going to have 3 comparisons here. So be consistent. Put all of these side lengths either in the top or the bottom. Let's say we want to put them in the top. So we'll start with that 32. And then we can show the 45 and then the 60. And for the other triangle, put all of these in the bottom, 22 and 30 and 40. And so grab your scientific calculator, see what these reduce to. And here we see 60 over 40 reduces to 3 to 2, 3 halves. 45 over 30 also reduces to 3 halves. And it looks like it's going to work out pretty well until you check the last scenario. When you reduce this, we end up getting 16 over 11, and that is as far as it will reduce. So based on the fact that these are not all the same, we actually don't have a consistent scale factor down. It's close. It's very close, actually. If this 32 had been a 33, I think it would have worked. But because as is, they don't all say the same thing, the sides are not actually proportional, even though it's very close. So the visual test would have fooled us here. So not similar based on our information. meaning we should not be writing a similarity statement and no theorem applied. Okay, so checking the sides, we'll check for that consistent scale factor. Now going to number 5, first tendency would be to say no, that these triangles are not similar because the angles don't match. But we actually don't know all the angles in order to make that claim. So first thing we really need to do is, in cases like this where you're given 2 angles in a triangle, you should really find the third angle just to see how things work out. Because so far, I do see a congruent angle here and here. So maybe there is another pair. Well, let's look. S and N, this 25 and 35 adds to 60. That would make this angle here at U 120. And here, these add to 145. So this missing angle here is 35. And if you look at the triangles, now we have all the angle measures. We don't have all of the angles congruent. Only that one pair of angles was. So not all angles are congruent. And that means that these are not similar triangles. So we won't make a similarity statement or claim any theorem. Okay, and I went ahead and revised my statement to say not all pairs of angles are congruent. Okay, so let's check this last example, example 6. It's very much like example 4, where you're given those 3 side lengths. And so if you know all 3 pairs of sides, we can check that theorem of side, side, side similarity. Let's see if all of the pairs of sides have that equal scale factor involved. So order them, figure out what your smallest side is in each triangle. So here's the smallest side here. And then this is the next one up, and here's the largest side. Okay, so smallest side here is 9. Next one up is 11, and the largest side in this triangle is 12. And so checking the comparison, we have 3 comparisons to investigate. So here's number 1, 2, 3. And looking at those, be consistent. So we can put all of the sides from this first triangle in the top if we want. So 18, 22, and 24. And for the other triangle, do the same and go in the same order. So we started with the smallest. Let's start with the smallest again. So we'll go from 9 to 11 to 12. And looking at these, do they all reduce the same way? You notice that we have a scale factor of 2 showing up. So yes, all of the sides are proportional, leading us to say that the triangles are similar. Triangle ABC should correspond to, if you trace that out, ABC takes us across the large and then across the medium. So doing that over here, that would be HKG. Okay, and the theorem that applied here was side, side, side similarity. And if you're watching this video, that's a pretty good stopping point if you're just looking at how to check that triangles are similar to each other. I'm going to, below here, show a few other cases of finding missing links, measurements of sides, that is. And so looking at these triangles in 7, there's some special setups. First thing I want to know is whether or not the triangles are similar. And so we see there's a pair of angles here and that are marked congruent, and we have these vertical angles in the middle that also have to be congruent. And so the triangles are similar by angle similarity. And if I know already that the sides are similar, then that should tell me that that the triangles are similar, then the sides should be proportional. And so comparing sides, we have to kind of look at how the angles are marked. So we have one angle here to one arc here to 2 arcs here, where the 2x is located. That would mean that we compare it to the 9 over here. And for the same reason, the 8 compares to the x. So setting up a proportion here, we'll compare 2x to 9. And being consistent, if I started with 2x, I'll start with 8. And we'll compare that to x. Okay. Cross multiply, 2x times x is 2x squared. And 9 times 8 is 72. Divide by 2, x squared equals 36. And you can either reason this through or remember that you can take the square root here to solve, and we get x equals 6. Okay. Looking at number 8, we have parallel lines shown. And if you remember this from earlier, with parallel lines, we have alternate interior angles that are congruent. You could do that with the other alternate interior angles as well. You could also show that the vertical angles are congruent. We don't have to do that. The requirements just show two pairs of angles, but again, angle-angle similarity is here. So the triangles are similar to each other. That means the sides are proportional. So comparing sides, you can use the arcs to help you out. 8 is between the one arc and the two arcs. So we can compare 8 to the side in the other triangle. It's the same way. That would be the 4. It's between the one arc and the two arcs. And then we can use the 3x plus 4. So 3x plus 4 to compare to the x plus 12. Practicing consistency here. The 8 was on the top, so the 3x plus 4 has to be in the top. Now cross multiplying, remember we do need to distribute here. We have 8 times x plus 12 equals 4 times 3x plus 4. And distributing, what does that give us? It is 8x plus 96 equals 12x plus 16. Okay, solving this, we can subtract 8x on both sides, subtract 16 on both sides, and we get 80 equals 4x. Divide by 4, and x equals 20. Okay, one last scenario here. With these triangles, we see that there's parallel lines. We have another type of angle that has to be congruent then. Remember, these are called corresponding angles. So corresponding angles are congruent. Okay, and we could use the other pair of corresponding angles over here, or we could realize that both triangles use the angle up top. So they both have that angle in common. Okay, so looking at your side lengths, pay attention to what the sides are for the small triangle. We have a 10 and an x plus 2. So we could start that comparison where we put both of those either in the top or the bottom of a fraction. So maybe we put 10 in the top of this one, x plus 2 in the top of this one. And we put the bigger triangle side lengths in the bottom. Now, if you're careful, you're going to notice that the side over here is not just 10, it's not just x, it's both of those combined. So it's x plus 10. So there's the entire side length on that side. And so for the big triangle over here, the side length is x plus 10, which we'll put with the 10. And the bottom is x plus 14, which corresponds to the x plus 2. Okay, cross multiplying here like we know how, we get 10 times x plus 4 equals x plus 10 and x plus 2. And this is actually some algebra here. You're going to get 10x plus 4 equals FOIL on this side. When you multiply, you're going to get x squared. plus 2x. And then multiplying by the 10, you get 10x and plus 20, which all this is going to simplify. We're going to subtract 10x and subtract 4 on this to move them over to that side. We're going to get 0 equals x squared plus 2x and plus 16. And there are ways to solve that. We're not going to worry about this one, but just showing you that it could happen. We could either solve by factoring, or we could solve this by quadratic formula. So I'm just going to make a note of that. Solve by quadratic formula. But that's not a main focus of our class here. Okay. And that is the end of our lesson on proving triangles similar. And we're just really focusing on those three theorems and whether or not angles are congruent and sides are proportional.